I'll start with the first question. Let me just. Yeah. So I'll go with the first question, which is very, I think, an informative one for the audience. So when we use tychography, so an audience seeks an information about this. What is tychography and when do we use?
Yeah, that's a really good question. Thank you. Yes. So it's a really emerging technique, and it's something that it essentially does imaging using coherent diffraction patterns. It has to be performed as a synchrotron. It's fairly specialized, but you basically, instead of doing absorption spectroscopy like we do in STIX-SIM or in scanning transmission X-ray microscopy, in tychography, we use coherent diffraction imaging. So you actually use the diffraction pattern. And I swear this question was not planted by Ajay, but there's a beautiful perspective on X-ray tychography that is appearing in just a few weeks by Stephen Urquhart from the University of Saskatchewan. So just stay tuned for that. It's actually a beautiful tutorial introducing the technique and its recent advances, and it'll be online in just 1 to 2 weeks.
Thank you, Professor Banerjee. So moving on to the next question. So one of the attendees would like to know the role of acidity on vanadium pentoxide and their metal salts.
So I think your question has to do maybe with synthesis. Under different pH conditions, you have vanadium oxides have a very rich Pourbet diagram. Okay, so at different potentials and different pH, you stabilize different vanadium oxygen clusters, and if there's different metals present, it becomes an even more complex part of this Pourbet diagram. So it's synthetically a challenge to make anything and to navigate that diagram to arrive at the product you want. But there's a lot of interest in doing so to improve so that you could get phase pure binary, ternary, even quaternary compounds of vanadium. And there's a lot of progress in that direction, some of it empirical, some of it guided by machine learning to arrive at the desired phases of vanadium using Pourbet diagrams as a guide.
Yeah. So we'll take the next question. So it's a series of questions, Professor Banerjee. So I'll start with the first part. Sure. How much are the structural features dependent on the way the cathodes are manufactured?
Yeah, that's a really good question. So, and I think maybe I should go back to a couple of slides. Maybe be able to go back. Right. So really, cathode design depends on. Let me see if I can. So cathode design really has to happen across multiple length scales, right? So the atomistic and electronic structure gives you a necessary set of properties in terms of redox properties and such, but not sufficient. The actual manufacturing of the cathode is tremendously important, and that's sort of what I kind of alluded to in terms of these mesoscale phenomena that are emergent as a result of particle geometry and packing. And so it's not just important to look at single particle phenomena. We saw several examples of that, but also to do probes, use probes like EDXRD, where we're probing layers per layer in a real cell or something that looks like a real cell, and looking at the effects of tortuosity and particle porosity and particle geometry on the cathode. And the entire thing is important both from the perspective of accessible rates as well as chemistry, electromechanics, electrochemistry, mechanics coupling, and so on and so forth. So you've got to start with a good material, but then you can squander the advantages or realize its potential in the electrode based on the manufacturing you do that puts together the particles in a three-dimensional electrode structure.
Yeah, so I think you have covered the second part, which was around how were the cathodes you described generated and laid down, whether it's a coating procedure or some other procedure. So I think you
Yeah.
have
So
covered. Yeah.
this is a really good question. And because we were comparing these higher length scales, we wanted to keep everything as constant as possible, varying just the particle geometry. So keep the coating specs exactly the same, while varying the particle geometry, so we could tease out these geometric effects.
Yeah. So the last part of this question, Professor Banerjee, is can the use of inkjet deposition of cathode materials onto the carrier substrate affect the substructure in a positive way?
Yeah, that's a really good question. So an inkjet, I would expand that to say any 3D printing method. I think there's lots of interesting opportunities for structuring electrodes with 3D printing. What needs to happen is of course, a lot of 3D printers work very well at slightly higher length scales. So we need to do a little bit better in terms of the finer sizes, dimensions that we can lay down using a 3D printer. So this is actually an ongoing area of research in my group. Got several students working on this. How do you come up with manufacturing methods that give you not just porosity that results, or tortuosity that is an indirect result of picking certain geometries and processes, but could you deterministically define those geometries using some sort of additive manufacturing method? So I think it's a very active area of research, and something that will be important if these electrodes realize their full potential.
Yeah. So, Professor Banerjee, moving on to the next question, can you please comment on the future prospect of single crystal vanadium oxides?
Yeah, so I think single crystal electrochemistry is really, I think, intriguing, because just like in protein chemistry is the analogy I like to give, right? Without protein crystal structures, people were still doing a lot of work, but a lot of it was indirect, right? And so in the case of cathode design, there's still a lot of very good modeling going on that allows you to get insight into atomic diffusion pathways, but it's really been very difficult to really know what is happening at the atomic level in terms of the pathways adopted by ions. So single crystals, I think, fill that urgent need to know how the structure changes and where exactly the lithium ions sit inside the structure, and how they migrate through. And because if you can identify the bottlenecks, if you can identify the pathways, the site preferences as the ions move through, you can modify the structure so that you can open it up, or do some very careful modifications, just like you would modify binding of a drug molecule to a docking site, right? So it gives you the ability to do atomistic control of these intercalation hosts that you don't have with other analytical techniques.
Yeah. So again, relating to the vanadium oxide, we have a question: why it is not used in commercial lithium-ion cells? Professor Banerjee, your insights, please.
Yeah. So I think there's the commercial use. We hope it will be used in commercial lithium-ion cells. There's a big historical issue as to why what was picked and what was not picked. It's clear that cobalt that was picked has a lot of challenges, right? Both in terms of the oxygen evolution that happens, but more importantly, what you see here, the real world applications of intersecting with earth abundance and supply chains. As most of you know, cobalt is mostly extracted in Congo, which has seen a lot of unrest, and really cobalt and accessing cobalt has destabilized large parts of Central Africa. So the reason we and many of our colleagues are very interested in vanadium is it's actually a very geographically diverse supply chain. You've got vanadium in Brazil, South Africa, Australia, Kazakhstan, and really many parts of the world where you can get high quality vanadium, China, of course. And so I think there's a lot of hope, and as we make new choices for cathodes, right? As we enter into this new world of lithium-ion batteries that are not just for small portable devices, there's a lot more room for diversity of materials in terms of what gets used.